Hello, and welcome to Agrosive Physics. Today is day 109, and what I'd like to discuss today is parallel plates. Now, we've already discussed the fact that an electric field in between parallel plates is uniform. We've also discussed the electric potential that exists at different points in a field. Now, if we have parallel plates, what we're going to notice is that the potential, because the electric field is uniform, is going to be uniform as well. So the potential is going to be, E is uniform inside the field, so thereby we're going to be able to find the potential between the top and bottom of the parallel plates quite readily. Now we're going to need to take our E equals F over Q equation and our V equals W over Q and combine them. And what will happen when we derive that is we'll end up with the equation V equals ED, and I call it VED. Now, V is the potential difference. Usually you connect the parallel plates to a battery or a power supply, and that could be anything from 12 volts to 120 volts to something in between. Could be even a 3-volt battery or something like that. And what we'll do is we're able to determine what the electric field is between two parallel plates with the V equals ED equation. Now, the reason this is important is because capacitors are typically built from parallel plates, and they're called parallel plate capacitors. And because the electric field is uniform in between, we can use this VED equation in order to calculate the field strength. Typically, like I said, we'll connect it to a battery. If we're dealing with a capacitor in a disposable camera, it'll typically be 2 AA batteries, so 3 volts total. If you know the distance between the plates themselves, usually what will happen is you'll have 2 pieces of foil. In between is an insulator so they don't short circuit, and they'll wind it up and put it in a small package. The capacitor is quite small inside an electrical circuit. Now, the reason you need a capacitor in the first place is because the flash for a disposable camera requires a lot of charge very quickly in order to operate. So 3 volts at a slow rate won't work. So you need to store up the charges and store up the charges, and the capacitor is going to allow that to happen. You have this gap in between the two ends of the circuit. Basically, you're creating almost a switch. And after you store up all that charge and you press the button, it'll allow all that charge to disperse quite quickly. Now, capacitors are a little more complex than just V equals ED. In fact, it depends upon what is in between the two things, called the dielectric constant, and that will be something that would be discussed in an advanced placement type course. But for our purposes, capacitors store a lot of charge. They work on the principle that parallel plates have a uniform field between them, and we can use the V equals ED equation to calculate the electric field strength. That will even allow us to maybe calculate the amount of charge that may collect at one end or the other. So utilizing our equations will allow us to solve more complex problems. And capacitors are a nice application of the electric field in between parallel plates. So at this point, we'll look at some sample problems dealing with parallel plate capacitors. We won't do too many problems of high level difficulty, but we'll keep it to typically level 1, maybe a level 2 problem. Let's take out the whiteboard now and look at some sample problems. Thank you. Now, if we combine the concept of electric fields and potential difference, we end up with a parallel plate capacitor. Now, a parallel plate capacitor is effectively something that can store charge. Now, right now, this is the parallel plate, and this will be a power supply. We're going to talk about this kind of symbol in our current electricity section coming up. But let's just say it's 6 volts. Well, that means we have a potential difference of 6 volts between these 2 points. Now, if we remember that V equals W over Q, that's our potential difference, and that in between parallel plates, and actually this would be positive and this would be negative, so it would be backwards. And we'll talk about that in the current electricity as well. We know that the field in between is uniform. So uniform electric field. Well, if we remember that V equals W over Q and that work is really force times distance over Q, then we have E, the equation for E was F over Q. Well, let's see what happens when we combine them. We have E equals F over Q and V equals FD over Q. Well, look at this. F over Q, F over Q. So if I divide this by D, we have E equals F over Q and V over D equals F over Q. So that means E equals V over D. And for some reason, I don't like equations that have division signs if I can avoid them. That's why I do F equals MA. You can rearrange this as V equals ED. So if you know the distance between the parallel plates and you know the potential, for example, I plug this into a 6-volt power supply, and this is 1 millimeter apart, let's just say, then I could find the value of the electric field. So the electric field, in this case, so it would be 6 volts equals E times 0.001 meters, and 6 divided by 0.001 gets me a value of 6,000. And what was the units for electric field? All right, it's force, which is newtons, over Q, which is coulombs, newtons per coulomb. So if we combined our parallel plate capacitor with our voltage equation, we end up with what I call the VED equation, V equals ED. So we can figure out the electric field in between the parallel plates of a capacitor, which will store electric charge and then allow it to be released quickly when we want it to be. It's useful in strobe lights and in disposable cameras for the flash.